So the last two lectures are on something called polynomial expansion. So that's like the topic for the last two lectures. What does it mean? We say that a graph class G is polynomial expansions if there exists a polynomial P such that for all radius, for all graphs into the graph class, like the distance are minor, the depth are minors of this graph have got density bounded by P of. Yeah. So the bounded expansion was that this is any function. Yeah. Like if I take another color, and if I want here to have got polynomial bounded expansion, then I will here say any function, and I will get this definition. And now what I do for polynomial expansion, I require this function to be a polynomial. Okay? And yeah, so that's like one of the up there, that's like the definition. So it's like a strict subset of the classes of bounded expansion. Yeah, we have got this picture of like having graphs of bounded expansion, graph class of bounded expansion. There are nowhere dense, nowhere dense, and up there, and the polynomial expansion somewhere inside here. Yeah, polynomial expansion. So it's smaller than bounded expansion, and what we can say is that hey, I mean, we can compare the different graph classes up here. Yeah? For example, we can say that, hey, remember that this one was actually constant for graphs, like the density was constant for graphs excluding a fixed minor. Because for graph excluding a fixed minor, you have got a linear number of edges in number of vertices, so you have got like constant density of any minor. So it's like excluded minor up here, and inside excluded minor, we have got, for example, planar graphs. Okay, they're here inside. But if you look for graphs of bounded degree, for example, bounded degree guys will be here. Okay, these are bounded degree. They are bounded expansion, but they're not necessarily polynomial expansion. That will show that. So this is like sort of like something which captures excluded minor, but doesn't capture bounded degree. And the problem is, I mean, one of the things that a lot of these graph classes come from graphs that are like defined in geometric fashion. We'll do some examples on the tutorials today and in the next week, but a lot of these things are not minor closed for some reasons. A lot of the such graph classes coming from some geometric objects, but they are of polynomial expansion, so we can do something about it. Okay? And what we can do is that, hey, we'll prove what happened. I mean, what can we say from this assumption? So let's do first the easy things. Well, what we'll do on tutorials is that the admissibility is bounded. Yeah? If G is bounded of polynomial expansion, then there exists a polynomial Q such that the admissibility R of G is bounded by Q of R for any R and for any graph in the graph class. Yep. That's what we'll do on that exercise. That's actually quite simple. The other thing is, of course, being a topological minor is more difficult than being a minor. So because nabla tilde R is bounded by nabla R, up to definition what does exactly R mean in the nabla tilde. I don't remember how exactly it's saying +1 times 2 or something like that, but I will put here like some way we think here, depending on whether like topological minor you have the paths of like 2R + 1 or R or something like that up there, but still like bounded polynomially bounded grads by the nablas for minors are bounded polynomially minors for being topological minor, and so of course like nablas are bounded. Yeah, nabla. There exists polynomial P tilde such that nabla R of G is bounded by P tilde of R. Yeah, so that's also true up there. Yep. So we have got these easy things. There are some things that turn out to be difficult and on tutorials. And yeah, so on tutorials we will investigate the following graph class. I want to show an example of something which is a polynomial expansion. It's weird. So let's define G T to be like graph G with every edge subdivided T times. So every edge gets replaced with a path PE of length T plus 1. Yeah? So inside every edge we put T new vertices. Okay? And let's look at the graph class, which is G strange, but call it G, is like we take any graph we want and subdivide it 6 times for any graph G. So we take the class of all graphs, but for every graph we look at the tree and subdivide every edge 6 times. Okay? That's like a class of graphs. It's weird, it's not closed under subgraphs, it's not closed under reduced, I mean, it's like non-trivial graph class. But what I want to say is that nabla R, on tutorials we will prove, but that's very difficult. On tutorials we will prove that nabla R of G is order of R, that the polynomial is linear there. It's like R, you can even do something like R plus 2 or R plus 3, but linear in R, nablas. But weak coloring numbers are exponential. Can be 2 to the some polynomial of R. Yeah, they can be like they can be exponential. So like we won't have a polynomial bound on the weak coloring numbers, even if the graph class has got linear expansion or like polynomial expansion. Okay, that will be done on tutorials. There's another example. You can also show that this graph class don't have polynomial bounds on the low 3 depth coloring. So they G may require 2 to the poly P colors for low 3 P color P center coloring. Yeah, so if you want the P center coloring or P low 3 depth coloring, and you want any subgraph on at most P colors to have 3 depth at most P, then you may need exponential number of colors in P. If you remember the proof we had for the P center colorings, it was like the weak coloring number, it was like the greedy coloring in the weak coloring ordering of radius 2 to the R. Yeah? And then the weak coloring numbers were somewhat like, sort of like nabla R to the R or something like that. This type of like, the weak coloring number was like nabla R to the R in our proofs, and then this one was weak coloring number of 2 to the R here, up there. Okay? So this was there's like twice the exponential way if you follow our proofs, but I mean, you won't get P-center coloring with polynomial of colors in these graph classes, in this graph class. So this is like a strange example. This is really a strange example of a guy which has got no good geometry representation. It has got polynomial expansion, but somehow like is a counterexample to like what you want to have here. And it's so what's left here, we have got admissibility here, bounded polynomially. That's not very difficult, we'll see on the tutorials. We have got a good example that contradicts weak coloring number and P-center colorings. The point is that here, in this graph class, the strong coloring numbers are bounded. Because the strong, this has got true up there, and like the strong coloring numbers are bounded by, I mean, the true is like the strong coloring number, the largest strong coloring number, yeah? Up there. So the open problem is that if G is graph class with polynomial expansion, does there exist a polynomial number P such that for any radius and for any graph class in this graph class, the strong coloring number R of G is bounded by polynomial of R. Yeah. So we know that admissibility is bounded polynomially. We know that weak coloring numbers may be exponential, but we don't know about the strong coloring numbers. That's an open problem. Okay, so that's thing we don't know. But what we proved today, and what's important for us, and why this graph class is really important, so this polynomial expansion was actually defined not really by the guys, I mean, it was suddenly people understood that the polynomial expansion is the correct notion, but it was really defined first by the guys working in approximation in a geometric setting, like computational geometry. Because the important property that we will have here is that if G has the polynomial expansion, and then there exists some constant delta, such that for any graph in this graph class, if we define the number of vertices to be P of P, there exists a balance separator of size order of n to the 1 minus delta. What does it mean a balance separator? Now I need to make some definitions here, but what's the intuition here? Remember that if you work with planar graphs, there's this theorem, this Lipton-Tarjan theorem of balance separator. That if G is a planar graph, then there is a set of vertices, there's a set inside V of G, that size root n, and whose every connected component is smaller than half or 2/3, like every connected component is G minus x, the size of C is smaller than, I don't know, n 2/3 n. Okay. I mean, there are many ways of doing it. You can do it by cycling the dual, there's many topological things you can add on top of it, but the basic thing is that if you have a planar graph, there's a way to split it into multiplicatively smaller pieces using only root n vertices. Like the hard case is a root n by root n grid when you need to cut the middle row or the middle column or something like that to get two halves. Okay, so that's like the planar graph, and what this theorem says, I haven't decided yet what the balance separation is, but that's the intuition here. It's not exactly that, but up there is that, hey, polynomial expansion is the property that gives us balance separators of sublinear size. Okay, and you can may have seen ways of using it for approximation algorithm. That will be do next week. But the idea is that, hey, the fact that this is root n is not that it's not the power half here and to the 1/2 is not critical for the usages of in approximation algorithms. This is sufficient for the usages of approximation algorithms. We'll see in a week. We don't see any approximation algorithms today, at least on the lecture. So this is enough for many uses in the approximation algorithms. So the polynomial expansion, would give us a lot of approximation algorithms like up there, because we can use these balance separators up there. So if you have ever seen the notion of an R division in planar graphs, this notion leads to the graphs with balance separator of sublinear size. And then a lot of things you could have done with R divisions in planar graphs, you could do with balance in graphs of polynomial expansion. And that's like why they are important. Okay, so let's make the definition so that I'm precise. I will be using the sort of graph minors type of definition for separation. So I want to say that if I have this graph G, then a pair AB is a separation if there are subsets of vertices G that together is everything, and there's no edge between A minus B and B minus A. And the order of the separation is the size of the intersection. What's the picture? The picture says more than words here. I have the graph, and there's the left side of the separation, which is A, the right side of the separation, which is B. This is the separator, this is the intersection, that's what we want to be small, okay? And there are no edges from here to here. There can be edges here inside, there can be edges going like that, there can be edges going like that, but there are no edges up there. So this is a way, this is the left side, this is the right side, and the things that separate is both on the left and the right, it's in the center. Okay? And now balance separator is really a separation AB, where nothing eats too much. So neither this wing nor this wing is large. So both A minus B and B minus A is smaller than 2/3. So it's both this wing of the separation, this wing of the separation are smaller than 2/3. Okay, so that everything shrinks a bit. And think if there's, and this is now not size, but we say here order. Yeah, so this thing is tiny, it's sublinear, and this is less than 2/3, and this is less than 2/3. So each of them is at least 1/3 really, because this is tiny, this small. Okay, that's what we want. Okay, good. So now we have our introduction, we have our motivation. The usage for approximation algorithms will be next week. The main point of today, and maybe it will span almost everything today, but maybe slightly less, and maybe I will say something at the end, is to prove this theorem. Okay, we want to prove this theorem. And how do we prove it? So now I want to go back to the beginning, and now I want to beginning of the board, and now I want to write a technical theorem that implies this. And we'll work with the technical theorem. So the technical theorem will be working. This is something, and you may have seen the name, you may sometimes see the names of plot mineral Smith. Because I think this, I don't remember the year, but that's quite the old thing, but so assume that we have got a graph G with n vertices, and we have got two parameters H and L. Okay? There we got a graph and we have some parameters. And this algorithm is a polynomial time algorithm. In polynomial time, either we compute either a large clique minor, so k h as L log n depth minor. So either we find a minor model of a clique of size h as L log n depth, at L log n depth, or a balanced separation of size, and the size will be complicated, n over L plus h square L log n. Okay. So this is like a technical statement that we'll spend the rest of the proof to do it. It's not super complicated, but quite a technical way of doing it, okay? So we don't have any, know that the good thing here is that we don't have any polynomial expansion, no nablas, no stuff like that. We have got just a graph, any graph with some parameters, and we say that either we find a large clique minor, the graph is dense, or there's actually a balanced separation, which is not like of size n. Like if L is super constant, then this is sublinear, maybe this is small enough, so that's fine. Okay?
Is this constant in O, hidden O, it depends on H and L?
No. This is like there's 5. I mean, I don't know if 5 exactly works, but we'll see from the proof that there's like, and it's not like super huge constant. No. Like, they're just integers, and because we just use it for far non-constant size. So let's try to apply it for polynomial expansion, okay? Because we don't expect too large guy as a too shallow depth minor, okay? We don't expect, I mean, H is also like the density of a clique minor, I mean, up to some constants, okay? I mean, the density is like H minus 1 or something like that, okay? So assume that we have got a graph class G such that, let's say that the density of R of G is bounded. I will write here something like a constant times R plus 1 to some power D. Okay? So I mean, this is like some generic way of saying a polynomial when R, we're worried about R's being like 1, 2, 3, etc. Okay? So there's, let's say that we have got this type of bound. Okay? Say I have got this type of bound. So what do we don't expect? We don't expect this one to be too dense. So we don't expect H minus 1 to be larger than C times L times log n plus 1 to the power D. Okay? We don't expect this outcome. That would be too dense shallow minor. Okay? Because that's like the density of a clique. That's like the number, maybe half, yeah, twice, yeah. So that's like the number of edges versus number of vertices in the clique of size h, and this is like what the bound on the nablas will say us. Okay, okay, that's what the bound on the nablas says. Okay, good. So we don't expect this one. So if we put h of this order, then we would expect this. So if we put h be equal like twice c L log n plus 1 to the d, we expect this outcome. We don't expect this outcome. Okay? So let's plug it here. Okay? So we have got order of n over L times, and there's this h square L. Yeah? And what I want to say here is that's roughly L L log n to the power, I don't want to, the exact computation is known, but there's something like d plus 1 here, maybe plus 1 here, and there's some constant c to the here in front of it. There's this c, no, this c square, 2c square, like 4c square. Yeah, there's like, yeah, I mean, I did some minor errors, like just to make this life easier. But now what's the point is that now, hey, we want this one to be sublinear, okay? So there's this 2d here, there's like this is yeah, there's one SR log n here, and there's like this one. So what we can do, we can put something like L, so we want L log n. I mean, we want this one, we want this one to be equal roughly to this one. So we want L log n to be roughly n to, this is 2d, so 1 over 2d, yeah, 1 over 2d plus 10. If we put something like this one, then, did I make a mistake? I don't think so. Yeah, so if I put some L log n to be roughly of this size, then this is like, I mean, let's put it, then this is like, then this becomes order of, yeah, so L is over log n. So I want to say that this is something like n to the 1 minus 1 over 2d plus large constant plus 100. Okay, and this is our delta up here. Okay, so what we are doing here is that we are saying, hey, okay, if we now have this, put this h, and then balance out these two arguments, there's L with some large power here, and there's L here. This log n doesn't make much difference up here. So now if we take L, a small polynomial like n to the tiny power, n to the tiny power like that, so that this one has got still smaller exponent than this one after division here, then we get this n to the 1 minus delta, and this delta is roughly 1 over d, where d is the polynomial we get here, 1 over constant t. Okay? And this is like play with the trade-offs with the numbers. So we say, hey, here if h, for h being roughly L to the d, we don't expect the first outcome, and we want the second outcome, we want the balance separators. So if we put L being something like n to the 1 over d plus 1, we balance out these two terms, so like 2d plus 1, we balance out these two terms and get a sublinear separator. But it's not plus 10, but plus something. I mean, if somebody wants precise computations of this exponent and how to make, I mean, not to be that lousy that I did here, there in the notes, but what I wanted to present here is the intuition behind these calculations. Yes, so that, I mean, yes, the h being a large polynomial in L is forbidden for this term, and then we balance out this term to be equal to this term so that we get n to the 1 minus 1 over this polynomial, more or less. Good. Good. So that's how we do it, and now our goal is to like prove this theorem. Okay, so my goal is like to now keep this statement, because at least I want to keep this formula here, and now wipe out these computations and wipe the theorem up there and prove the statement. Okay. Let me check time. Good. An hour, that should be fine. So I'm wiping out this computation as well. They've been recorded, so we're happy. Yep, and we do this. So what's the intuition? I mean, let's look at this bound. What's this one? We're looking for L log n depth minor of kh. Okay? How does this depth minor look like? This depth minor, there are some branch sets. Okay. There are h of them, and they're of radius L log n, and there are some edges between them. Now I have wisely chosen the first guy that's on planar, but okay. And there are some edges between them. Okay? So what's inside these blobs? What really matters inside this blob? Inside this blob, it matters only to have some tree that connects all these pieces. Okay? So this blob, it can be just thought of as a tree that connects these entry points to the other guys. Okay? So this tree is really of size h minus 1 times L log n. At most this size. Yeah, because I mean, this is the distance to the center, and I need to connect this number of connections. Okay? And there are 8 such blobs. Okay? So our minor model of this depth of this thing is of this size, h times h minus 1 times L log n. Okay, that's the size of our model that we are looking for. Okay, because I mean, inside the blobs, it only matters to keep like from a center path to like entry points to other blobs, one entry point for each other blob. Okay, so this part is really the part that we'll be trying to construct a minor model and keeping this minor model as the separator, as part of the separator. Okay, this is really like the bound of the minor model. We are constructing minor model, and once it reaches size h, we say, hey, we have got this outcome. Otherwise, we keep it as this partial part as part of our separator that we'll try to expand. Okay, that's like explanation of this term. Good. Good. So what we are doing now? So what's our goal? What's our stuff? So we'll be doing some recursive, like we try to some localization. We try to find this separator by some like building something inside the graph. So now we need to define or like look what we are trying to do. Okay, so what we will be doing is that we'll be our parts of like status of the construction. We'll have some minor model. So we have got some cage minor model of depth L log n of some kh hat for some h hat smaller than h. And as we argued here, these branch sets are of the size. Yeah? So this is of size h size branch sets of size h size minus 1 L log n each. That's our minor model. We'll call it M. Okay, we'll construct some minor model. Okay, so this inside the graph, this minor model will live somewhere here. There will be like it will, let's say it's orange for the proof. So there is some this minor model. We have got branch sets, some connections, blah blah blah. This is the minor model. Okay. Okay. Then, apart from the minor model, we'll add some extra guys to the separator. So there will be some extra guys to the separator x. So there will be some extra guys to the separator x. There are some extra guys in the separator. Okay, and there will be some parts that are trashed. There will be some parts that were already removed as the rest. These are like the small parts of the graph. They won't accumulate too much. They're like, so what we are doing here, we're trying to find the balanced separator. So we're taking some parts of the graph, which will be quite small, okay? Will be smaller and smaller, okay? And this extra separate, and this they were quite small, this is like less than third, okay? And we'll be separating of them, but it's the points that at every point we'll have some separation of correct side, and this will be like one side of the separation. So like the left wing of the angle is like a minus b, but during the construction, this side will be too small and this side will be too large. Yeah? We think of this one as being a minus b and this side as being b minus a. This side will be too small and this side will be too large. Okay? And we'll be trying to like push ourselves towards the larger side. Actually push the minor model towards the larger side, and either the minor model can be extended towards the larger side, or we can add something to x and split the larger side nicely into smaller pieces. So what we'll be maintaining here is that, rest, the neighborhood of the rest, is hidden in x union the model. Yeah, so it's really like a part. This is some part of the graph whose all neighbors are in the model in the x. So like the model and the x are the like separator up here. The rest is always tiny, so the rest is smaller than n over 3. Okay, so we will never exceed, the rest will never exceed. So I will put here for technical reasons 2 n over 3. But the intuition is up there that, hey, r will grow, and whenever r exceeds n over 3, we are done, because that's our separation. It will never do one jump from less than n minus over 3 to something much higher, like much larger than 2n over 3. But once we exceed 2n over 3, we are done with the separation. And we'll maintain the fact that x is smaller than r over r, L. So that's our charging thing. We are putting some things on this blue part, violet part, this blue part, some parts that will be like on one side of the separation, but on the same time we're putting something in the middle of the separation, okay? And the point is that whenever we put something to the separation, we charge it to some guys that we put on the R side. Okay, we do charging. And we put it on this R side, which means that this in the end, this X will accumulate here. Yeah, because R will be half of the graph, roughly half of the graph in the end, and X will be half of the graph over L, like 2/3 of the graph over L. Okay, so that's like whenever we separate, we want to separate with like 1/L fraction of what we chopped out from the graph. So we want to chop out small pieces from the graph, paying 1/L fraction of what's up there. Okay, and apart from that, there's this minor model that we try to build, and this minor model is this part of the separator. Okay, so that's like our thing, and in one step, what we want to do, we want to try to extend the minor model a bit. Okay, we want to try to extend the minor model a bit, maybe discard some things from the minor model, but try to extend the minor model a bit. Then, and whenever either we succeed in extending the minor model, and maybe some things become smaller here, or if we fail, we say that there's an option of like killing a small part of the graph to separate some larger parts. Have this 1/L threshold. Okay, so let's say that we have got this picture. Okay, so when can we finish? Well, what I said here is that if R is 1/3, we can finish. So first thing is that if R is larger than n/3, we are done because we set A to be like model plus X plus R, and B to be the graph, or the graph minus R, and because the neighborhood of R is hidden in X and model, this is a good separation. This is a good separation. This is a good separation, and it's a balance. I mean, the order of the separation is m plus x. So this is small, like it's the size of the separation, like the size of order of the separation. This is like, which is as we argued h hat minus 1 log n plus size of R over L, which is what we want. Yeah, so that's the separation, and because R is between 1/3 and 2/3, we are done. Yeah, because R, which is like A minus B, is between n/3, is between n/3 and 2n/3. We are done because it's less than 2n/3 what we require, and because it's larger than n/3, B minus A cannot be larger than 2n/3. So that's fine. So we finish when this guy reaches third of the graph. Okay? Also, I want to say that we finish if here all the connected components are small. So for every connect C, which is a connected component of like G minus like the things in front, yeah. So this minus X minus minor model minus R. Yeah, so we delete all these guys here and we look at this part with connected points. The size of the things is less than n/3. Yeah, if this piece gets chopped into small pieces now, where each piece is less than n/3, we are happy. Why? Because we can just add to R some guys. Like, what do we do? Like, pick this component C1 to C, I run out of letters, CA, okay? And take I minimum, such that R union C1 union CI has got size larger than n/3. Exceeds n/3. Okay? Like, take these components and add to R one by one. If I add a component of the rest and put it to R, take a component and like color it. Alright, I don't violate anything here. This is still fine because I took the entire component. This is still fine because, I mean, that's bound on the side of X. R is larger is better. And this, I won't break this one because at one step, I never exceed n/3. I never put one more than n/3. So if I'm below 1/3, and I add components of 1/3 one by one, at most 1/3 by one, at one step I won't jump over 2/3. Yep, I mean I will, at some moment I will reach more than 1/3, but I will never exceed 2/3. Okay, and then I proclaim this is new R. and go back to 1. Go to 1. Okay? Okay? So the only problem is that here there's actually some huge connected component. Maybe there are some tiny connected components. But there's actually some huge connected component C, which is of size more than a third of the graph in the rest. And what we want to do, this is the moment when we want to work. This is the moment when we want to say, hey, let's try to expand in this direction. Okay, let's try to expand in this direction. Okay? So the goal is now to like, let's go there, and like the goal is like, so the interesting case is that there's a component C, so I connect the component P minus X minus M in rest, such that C is large. That's like the interesting case. Okay? So now we want to do the following thing. So we want to like, this is larger. So now, of course, we want to say that this component is actually much larger. I mean, what I want to say is that, hey, there's this large component, so I can put the rest to the R. Yeah, because this is larger. What I can do, I can say R that becomes V of G minus X minus the minor model minus C. Yeah. On this picture, I mean, this is the component, so these guys I can color. Well, I won't exceed 2/3 by putting them up there. Yeah, I won't exceed 2/3 because this guy is 1/3. Okay, so I put all these guys on the R side, and again, if R is too large, if R exceeds 1/3, I can go to 1. Yeah, so whenever R at some moment exceeds 1/3, I go to 1 and I'm happy. Okay, so that's like up there. So I have got this C is actually a really big part of the graph, and I want to move forward. Okay, so what I do here, hey, let's try now to so what we want now to do is that we want to extend the minor model. So let's draw this picture close. So there's this part in here, and there's this minor model that looks here. Yeah, and it has got these blobs here. Yeah, there's these blobs, and I have got edges in between. And because again I draw a K5, I won't draw to all of them because they're not planar. Okay? And some of these blobs neighbors C and some don't. Okay? So some of these guys may have got edges towards C, but some of them don't. Okay? Okay? So now if I want to extend it to a minor model, I have got some chances of drawing a new blob here, but only the one that sees the blobs, the branch sets that see C. Okay? I have got no chance of extending these ones. I need to forget this guy. Okay? I need to take this guy and move him to R. Okay? I need to take this guy and move him to R and then say, hey, that's actually like, that's the only thing. So the first step what we do is that for every branch set B of model, if the B doesn't see C, move B to R. And this is again fine, because now C is the complement of R really. I mean, everything else was already moved to R. So now taking the branch set and moving to R, I mean, still R is the set of connected components. Still the neighborhood of R is like the model plus the set X that lives somewhere here. There's the set X somewhere here. Okay? Up there. The only problem is that we can move these branches one by one. If you do correct calculations, I mean, at one step we do like HL log n. You need the assumption that you will like HL log n is not like 1/3 of the graph. I mean, of course, the lemma is obvious if HL log n or h square of this, if this bound is h square L log n, the size of the, if this size of the minor model is linear in the graph size, the lemma is triggered because you could just put everything into the minor model, like into the separator. You can just put the entire graph in the separator. So like moving one branch set one by one to R cannot jump us from 1/3 to 2/3 by one step. Yeah, these branches are small. Because if they are not small, then our bound for the size of the separator is actually linear, so we could just kill the whole graph of our separator. So we can move these branches to R one by one. If we exceed 1/3, go to 1, we are happy. But At some moment we respond that everybody was moved to R, so this is like colored string, and we have got in our minor model everything attaches to C. And now let's try to make a new branch set. This is connected. We can make a branch set here. There's only one problem here. The only problem here is that if this one has got too large depth. Yeah? So let's try to draw this minor model with the color I haven't used here on this picture. So start from this point and let's like make a BFS. So let's make BFS. This is BFS. And in this BFS tree, you somehow like attach to these guys. Okay? You make this BFS tree and you try to attach these guys. And there are two cases. Either within L log n steps, you have already seen all these guys, so you have got your branch set, or after L log n steps, your BFS still continues and still haven't seen all the entry points to this branch sets. Okay? So you construct the branch set by BFS. You take one of these entry points, make a BFS, and make the subtree of the BFS tree that looks into this other entry point center. Okay, so like let's try to write it down. I think I want to go back here and redraw the big picture and like make it slow. I mean, make not only on the picture but like try to write something actually. Yeah. Okay. So what we do here, we have that we reach the properties that is by. So what we did here, like we moved to minor model, so we have got now the property that for every branch set on BM, we select some edge EB, which is an edge between UB and VB, so that this guy is in B and this guy is in the component C. Okay, so there's like this is the pink edge stuff there. There's like there's this guy, this is C. There's this model that looks like this. Okay, and there are the edges. This is B, this is UB, this is DB. Okay, and this is like, yeah, and there's this edges up here. Okay, we select some edge. We select some edge. Yeah, select some edge like that. And like make a branch set. So select up there and kick some E0 inside the model B, some branch set, and make a BFS tree from VB0 in this component. Yeah, so this is the green BFS tree. These are the BFS levels, and there's the BFS tree that somehow like works like this, and some moment it sees all the yep. And we have got case 1. Yep, so case 1 all BBs for B in the model are in T at level at most L log n. Okay, at most L log n. Yeah, so we see all these guys at level at most L log n. Okay, we see it's guys. Then we construct the new branch set. Yeah, then the new branch set B tilde is like subtree of T with root at VP0 and containing all VBs, and like this is a new branch set. So like now unit B tilde is a click minor model of depth. Yeah? So we tried to construct this branch set by BFS, and hey, if this BFS was short, after a few number of steps it visited all the guys here, we are happy, we have got a new branch set. Okay? And we somehow progressed, yeah? I mean, we went into this connector point C, and we like eaten up something. Maybe something very tiny, but we eaten up something. So we made the progress. Yeah? This component C, which is like this large component in front of us, shrunk a bit. I mean, we eat up something from it, so we made some progress. Yeah. In a sense, the progress of the algorithm is the size of the largest connected component of the remaining part. Yeah, because we always look at this largest connected component and we try to dig into it a bit, like scratch it a bit at least. Okay, and that's like our progress what we made here. Good. So that's like, and we try to scratch it so that we don't want to jump, so that we won't make a huge jump and suddenly the huge connected component is behind us. We never want to go from below 1/3 to above 2/3. Okay, that's like the intuition here. Okay, so that was the easy case. That was the case that extends the model. Now there's the trick that if the BFS progresses for too large, there's this more way of cutting it by using 1/L vertices so that there's one part is like large. Okay, so let's try to do this BFS and yeah. Okay, so I want to wipe out the easy part. Let me know already when we will finish. Okay, so case 2. And what we will be really using the fact that the depth of T is large. The depth of T is larger than L log N. So it's actually like the BFS really had a lot of levels. Okay? So let's draw this BFS levels. We used this color up there. So this is like 1 level, level 1, level 2, level 3, up to level A, and A is larger than L log N. Okay, this is our BFS. Okay, and what we want to say, hey, what happens? What I want to say is that, hey, let's try to grow. Think of this as a ball growing. Yeah, there's a ball of radius 0, then a ball of radius 1, of radius 2. This BFS like grows a ball from this root. Yeah, this is like this VB0 up here. Okay, it grows a ball, and I want to say that a nice moment is that you grow this ball, and suddenly the new things that you grow, like, so this is like level 0, okay? So I want to define a level at most I to be the union of j from 0, I, L, I, Lj, yeah? So L, J is that. So what happens what's nice is that when the new layer is quite small, when Li is smaller than size of L less than I over L. Okay? Less or equal. Okay? So what I want to say is that, hey, I'm growing this ball, and suddenly the newcomers to the ball is only a 1L fraction of what was before. Okay? The newcomers. What I want to say here is that, hey, now I'm tempted to say that L less than I goes to R and Li goes to X. Okay? If I have this one, if I grow this ball, okay? I grow this ball, and at some moment, the boundary of this ball, the new guys in the ball, the boundary of this ball is only 1L fraction of what's inside in this ball. So I'm tempted on this picture that was here before. Let's draw this picture again. So this is like the graph here, and there is the model here, and there is the separator X here, and there's the rest here, and the separator should be orange as well. Okay, and there's the layer in here, and suddenly I have got this moment that the boundary here, the Li, is only 1L fraction of what's here. Okay? And what I want to say is that, hey, put this one into X and this move to R. Okay? And now I have got my charging scheme, because the new guys, I charge what I put here to the new guys here, and this is like 1/L. Yeah? That's like, if I find this layer, I'm good, except for one problem. Yeah, I mean that works for the charging. Yeah, I'm growing this ball, and I'm looking for the moment when the guys on the boundary on the ball is just 1/11 of what's inside of the ball. Okay, and I want to say, hey, if this one's, then putting the inside into the R, into like the small side of the separation, and putting the boundary into the separation, to the cutting part, is good for our charging, because I put on the small side L times more than I put in the boundary, and I'm happy. The only problem is when this one is already like everything in the graph. I mean, there's a problem that I started with less than 1/3, and I don't want to make this huge jump when I suddenly has it 1 and 1/3, and suddenly the rest is like almost the entire graph, like 3/4, more than 2/3 of the graph. Okay? So the problem is that, so I can move this ones unless this is too large, unless this Li is more than half of the L less than I, is more than half of the component. So the point is that if I'm beyond half of the component, I cannot do it more. I mean, the point is that if I have got the rest, which is less than 1/3, and I have got this huge component in front of me, it's safe to put half of the component to the rest. Yeah? I have got this one, this on this picture, yeah? I have got this is less than 1/3, okay? And I have got this huge component here, but if I take half of this component and move here, I won't exceed 2/3. That's the important thing. Like, the important observation is that R plus half of the component is less than 2/3 n. Yeah, because this can be at most 1/3, and this can be, so this is like at most, I mean, it's like 1/3, and so we have half of the 2/3, and this is 2/3 n. Okay? So it's safe to move half of this component to the R side, but more is not safe. Yeah? So if our ball that grows is less than half, we are still safe with this step. Okay?
How do we know that C is at most 2/3 of N?
We don't know, but I'm saying that if R is smaller, then this, I mean, this like in total R and C is the entire graph, and we take this one with the factor 1 and this one with factor half, with coefficient half. And together is at most n. I can do, if you do on the math, this is at most R half plus R plus C half, which is, this is 1/6, and this is n half. Yeah, but the intuition is that, hey, this is a linear combination with coefficient 1 here and 1/2 here, and this is at most 1/3. So the worst case is this is 1/3 and this is 2/3, and then this is 2/3. Okay, that's what I tried to say here. Good. Yeah, so we can, so this works. This works until this BFS hits half of the graph. Okay? And we draw this BFS, and until we reach half of the graph, it happens that some layer actually, like the newcomers are only 1/11 fraction of what is before, then we can do the step. But once we reach half of this component, when we eat half of the component, we can no longer do this ones. But now the trick is that we can do the same from the other direction. Yeah? We can do exactly the same, so let's move here. So what's another nice, also nice is if this layer Li is smaller than what's later in the BFS over L. Now, what we could do, we have this picture, we draw this thing, but this layer where we're looking here is very late. It's up here. Okay? This was eaten by the BFS, and now this is the new level of BFS, and it's like up here. Okay? It's up there, and this is less than half. This is more than half of the component. Okay? But now what I can do, I can move this part to R. Yeah, I can do R union L is more than I, and X union I. And again, the charging scheme works, yeah? Because, I mean, I added some guys to the rest, of the small side of the separation. I added some guys to the separator, and for every guy added to the separator, I added L guys to the small side of the separation. The charging scheme works, and the point is that we argued here that adding half of the guys from C, is still fine, and either this one or this one, is smaller than C. Like for every level, either what's in front of us is less than half, or what's behind us is less than half of our component. So whenever this happens, I mean, we grow this ball, and first, until we reach half, we look whether what's behind us, the boundary is 1/11 of what's behind us, and once we exceeded half, we look whether the boundary currently is less than 1/11 fraction of what's in front of us. Okay? But how long can we do it? So let's try to do this. I mean, how long? Yeah. Some of the question is like, okay, what can now bad happen? What can bad happen is that, hey, we do it, and for the first half, until we reach half of the graph, we never do this, we never encounter this ones, and later, when we eat the rest, we never encounter this. Okay, so let's do this one. How long we can do this one? Yeah? So the bad case is that while size of L at most I is less than, I mean what we put in R, yeah, so less than I. It's less than half. We have got size of I is larger than size of L less than I over L. Okay? So what does it mean? It means that our ball grew by a factor 1 plus 1 over L at every step. Okay? Good. So like L0 size 1, but that means that Li is larger than 1 plus 1 over L to the power I. Okay? Okay? How long can we continue this?
L log n.
L log n times, because we at some moment we have n, we run out of vertices of the graph. Yeah? So this can continue only for L log n steps. So this phase, when we grow the ball, we haven't yet reached half of the component, but at every step we learn 1 over L new guys, can go only for L log n steps. Okay? And exactly the same argument is from the other side. Yeah? If we go now from the backwards, we go like bottom to top in the BFS, and at every step we include the new layer of the BFS, and every step we learn 1 over L of new guys of what was below, this also can continue for L log n steps. Okay? So what we have proven here is that the depth of the depth of the BFS is most 2 L log n. What means here that we screwed up some constants, but they're not very relevant. Yeah, I mean we should have put here like a 10 here. If I take now another color for fixing stuff, for fixing constants we screwed up. But if we put here, I deliberately didn't use these constants just to make our life easier. But if we put here because there's this O of n over log n, yeah. So if we put 10 here, then we have got this charging scheme with constant 10, like the x is r over 10, like 10r over L, yeah. Then we have got here also 10. Then here we have got 10. And here we have got L over 10, okay, because that's like, there's bigger factors, so this can continue over to L over 10 times log n rounds, so we have got L over 5 here. And we have got contradiction, because our depth was L log n to start from, and here we have put L over 5. Okay? Or alternatively, you can say, hey, actually here, I mean, we have a depth 2 log n, I mean, slightly larger depth of the minor we want to find, but it's easier to get no constants in the depth of the minor so that we can then apply the polynomial bound and have a constant scheme. Yep, so to summary, we have got here the following tricks. Yeah. Oh, so that was actually faster than I expected. What's the tricks up here? I mean, the tricks are we're trying to make a separation and we're trying to build the minor model. So what we are building here, we have got this like win-win situation. Either the big chunk of the graph that we're trying to decompose in front of us has got small radius, the BFS is depth shallow, so that we can find a new branch set of shallow minor, or this BFS is long, that means that this ball growing argument actually finds a separation with a good charging scheme, that we can chop off less than half of the graph of the remaining part by paying only 1/11 of what we chopped off. Okay, that's like the point, that the ball growing argument here says that we can chop off less than half of what's left by paying only 1/11 of what we chopped out. That's what we're doing here. And by inductively chopping off these things or growing the model, we either at some moment we grew the model because we too often made a small radius part so that we could grow a model, or we actually like managed to chop it off into small pieces with the separations, and we have got our separator. Okay, that was a difficult proof. I actually thought it would take slightly longer, but let's continue then. And let's now try to go back and see the big picture. Okay, so I'm wiping out everything and trying to solve the big picture. Okay.
So actually here we constructed a shallow minor of a clique. Does that mean that we can equivalently characterize classes with bounded expansions as those which do not
Yes.
have shallow?
Wait 5 minutes, yes. That's like, so what I wanted to say, I wanted to make a detour here. So this was like a Plotkin-Rao-Smith paper, which is quite old, but there is a paper of, I think, Dvorak and Norin. Hope I didn't screw up anything. This is recorded. Dvorak and Norin. That says that there's actually converse. If G is subgraph closed, closed undertaking subgraphs, and has got sublinear separators, so has got this property that there is some delta such that every G in G has balance of size order of n to 1 minus delta. Yeah, so this is like exactly what we proved, yeah? That there is some like sublinear function, like strongly sublinear. That means this is usually called like strongly sublinear separators. Separators. Strong sublinear means that there's really like exponent gain. It's not n over log n. There's some exponent gain here. The strong sublinear separators. Then the only way it means that this is a polynomial expansion. Yeah. That for subgraph closed graph classes, the only, I mean, this is like if and only if. We have got polynomial expansion. We have got strong sublinear separators, and the other way around. Okay. So this is like. This is the correct definition for strongly sublinear separators. If the strongly sublinear separator is exactly the tool we need for approximation algorithm, graphs of polynomial expansion is exactly the notion we want to look at. This is the class of graphs when these techniques apply. Up to subgraph closed graph classes. Okay? And now the comment from the audience was very targeted that I actually proved something stronger. If I defined like differently polynomial expansion, if I define polynomial expansion, like second definition of polynomial expansion is poly expansion prime, so poly expansion with a wave, yeah, that means that G direct is the polynomial P, so that for every radius and for every G in the graph class K P of R is not a minor of radius R of G, yeah? Not. Yeah, so like the largest clique minor at depth R is polynomially bounded in R, then we have got sublinear separators. Yeah, that's exactly the same proof. I mean, this polynomial behaves slightly differently. But what we did here is that we really looked at the clique minors of shallow minor. So we really excluded this one. And what this theorem says is that there's no, if you look at subgraph closed graph classes, there's no difference between polynomial expansion with the wave, with the definition. Yeah, a graph class has got a bound on nablas polynomial in R, if and only if it has a polynomial bound on the largest clique minor of depth R. Okay, barring the subgraph closed, which is the reasonable assumption. Okay, so it is true that it's like same. So what we actually proved is that we proved this ones from this one to here, and the result that's polynomial expansion actually equivalent to for subgraph graph classes to being So having strongly sublinear separators says that really doesn't matter whether we look at the largest clique as a depth R minor or whether we look at the density of the guys at depth R minor. Which is somewhat surprising, at least for me. Given the fact that nowhere dense graph classes and bounded expansion graph classes are significantly different notions up there. Good. Okay, so I'm left with some comments. So I want to make a comment on the R divisions. So I want now to apply our tool. This will be like this is an advertisement for the lecture for the next week. Okay, but this also may be useful in the homework. What I want to say here is that let's fix some threshold. It's really called R, so let's call it some fish R, but R is the radius here, so let's put in the letter rho. Rho is different. Let's have a graph G, which is in graph class G. This graph class has got this is subgraph closed of say strong sublinears. So these are separators of order of n to 1 minus delta, and it's subgraph closed in the sense that I want to say that all induced subgraphs will have got all induced subgraphs of G have separators, like subgraph of G of size balance separators of size of G of H to 1 minus delta. Yeah, so there's like, I mean, I have got a graph with sublinear separators or induced subgraphs have a strong linear separators. Think planar graphs. Planar graphs with delta half. This is it, yeah? Okay, so this is this one. So let's put some thresholds. And it's not necessarily a constant. I mean, in many options it's like, for example, like log to the 10 or something like that. I mean, it can be like some strange number depending on your needs, or like root n or n to the epsilon or something like that. So think some thresholds. And let's like make recursive decomposition. Like let's hit the graph with sublinear separators until it has got size rho. So we build a tree. So formally we build a rooted tree, wherein with every node t we have got some really induced subgraph of the graph V of G. So A root is the entire V of G. And what we do, and our argument is like while there exists some t such that size of AT is larger than rho, hit it with sublinear separator. So find A was a wrong number. C. Sorry, I will change it to C. Apply like AB. AB is the strongly sublinear separator for G of CT. Okay, and make two children, so T gets children TA and TB, and CTA is A minus B, and CTB is B minus A. Yeah. So I have got a node of my root that has got some big set. I hit it with sublinear separators and make two children, and one children gets 1/2 and one children gets 0/2. Okay? And that's like decomposition. And I stop if I reach depth R, depth rho. Okay? I think I need, no, I will put the entire A and B, I think. I think I need to put the boundaries or not put the boundaries. We'll see what's better. I think that one will be slightly better. Put the bound. I think I need to keep the boundaries. Okay. So now the point is, now I want to think of, okay, I look at the leaves of the recursion. So I look at the leaves of the tree. So I make a family X, which is CT for T is the leaf of this tree. Yeah. And the point is that, of course, for each C in X, size of C is smaller than rho, because I mean that's our stop of the recursion, okay? But it cannot be much smaller, yeah, because at every step we split into two pieces, yeah. So it's like it's really larger than like some one third of row. Yeah, I mean it cannot be smaller. So it really are around the pieces are around R, okay? The pieces are around R, around row, okay? But I want to count what's the total size of the pieces. What's the total size? How to compute it? Okay, because this is generally the entire graph. It's more or less the entire graph, but some vertices got repeated. When we split, these vertices got repeated. Okay? Yeah, these vertices up here got repeated. Yeah, so if we take a set, and if we take one set, and this is like CT, we duplicate this guys in between. Okay. Now I need to think if I will manage to do. I wanted to hit. I'm slightly worried that there will be some problem with calculation, but let's count that. So what I want to say is that yep. So let's look at one piece and let's look where from one piece where it got double counted. Okay, what's inside got double counted which levels. Okay, so what I want to say is that it's like it grows by at every step. The graph shrinks by a factor of like 1/3, at least by a factor of 2/3, and we double count like a sublinear factor of there. So okay, so this is like I want to say the following: sum over c side x, the interior of x, so like the unique guys of. So I want to, for every side of x, I want to define the interior of C to be the guys that are only in this piece. This is like C minus the union of x, C prime in x minus C. X minus C, C prime, and the boundary of x. Boundary of C is like the C minus the interior of C. So like the guys that appear in everything, so I can count the boundaries separately, and the boundary of C up there. This, the first thing, sums to the entire graph. So this is this entire graph plus the sum over C inside of x, the boundary of x, boundary of C. And now I want to say that, hey, at every step, it's really like, okay, so let's count for any C how much boundary it gets. It gets the boundary from his parent, from grandparents, from his great-grandparent, like the overlap between them, and the boundary of C, I want to say that this is the sum over ancestors, so like the Ci, the ancestor of T, where Ct is T, the ancestor of T, the size of the separator. So this is smaller than the size of the separator. So this is like size of Ct to power 1 minus delta. Okay, so I go up Ti. I go up the tree and count the separators up there. What I get. Okay? I count the separators, and I count the separators, and this one, yeah, and the point is that whenever I go up, I multiply by a factor of 2/3. By a factor of like 3/2. Yeah. If I go down, my pieces shrink by 2/3. That's the property of the like balance separators. The pieces shrink. So this is really a geometric series. This one is really a geometric series. It goes up, and it's really a geometric series. So this is like this is the wrong way of doing it. I'm worried now. I thought I think I missed some trick here. So it's wrong because that's like the top guy, and I want to count the top guy only a few times. Okay, I think I don't want to think in front of the board with this one. I think I missed up some things. Let's do another.
In odd levels, maybe separate just based on boundary.
Yes, I thought I could do without this one. I can do this one. I mean, that's one of the options to solve it, but I thought I could do it without this one. So one of the options that I was saying is that at every one step divide the entire graph, and the other step divide the boundary. Look at the current boundary and divide it in smaller pieces so that the boundary is always small. That's one way of solving it. I thought if I just want to count the sum of the boundaries, not individual boundaries, then I could do without this step, but I think I got messed up now. So I suggest now to stop, I will recover, and then we meet the tutorials and maybe we'll fix, because that was like extras, and I will fix it next week properly with the approximation because I need to repeat it anyway. But what I want you to remember here, sorry for messing up the proof, because I thought I can do without it. So the idea is that how we use in the approximation algorithms, that we take the graph and hit pieces with these sublinear separators until they become small. And now the point is that the boundary on the way here was quite small compared to what's up there. So we can modify the solution, the optimal solution on the boundary, and inside each piece, because it's small, solve it optimally, or do something smarter because it's small, or do some super-polynomial because it becomes small, or do some algorithm which is not polynomial in the entire graph, but on a piece it becomes polynomial, and then do some greedy part on the boundaries, or do something on the boundaries where and because the boundary is small, you pay only little up there. So that's like the typical use of sublinear separators, and sorry for messing up the proof. I will formally fix the proof next week, but we can also discuss it during the tutorials up there. Good. So I want to stop now, thanks. Shall we meet the tutorials at 2 instead of 2:15? Does it make sense? Okay, so let's meet at 2 for the tutorials, thanks.